What's going on, Rob Ma? Back at it with another video. Today I wanted to discuss a concept that I feel like a lot of scholars have been struggling with, and that would be long division. And I'm going to give you a couple of examples that I believe illustrate properly how long division works and what you should look for or what you should expect in your answer when you are doing long division several times and repeating the process several times. So let's look at a couple of different examples. The first example I want to go through is 1/8. Now, as we know, a fraction is also similarly a division symbol if we divide this number here by this number here. We divide the numerator by the denominator. So, how do we divide this? Very simple. We know that the bottom number is what is on the outside always. The denominator is always on the outside, and it's dividing into our 1 right here. So, long division, we know the process, very straightforward. So we know that 8 goes into 1 0 times. So we have to add a 0 here, because you can always add as many imaginary zeros as you want at the end of a decimal place. So we have 8 goes into 1 0 times, 8 goes into 10, 1.0 or 10, 1 time. So we know that. We repeat the process, we have 1, 8 goes in once, so it's just 0.8. So what we're left with on this side is 0.2. Now we repeat the process one more time. How many times does 8 go into 0.2? It goes in 0 times. But how many times does 8, if we add in another imaginary 0 here, how many times does 8 go into 20? 8 goes into 20 2 times. So what we were left with here is 0.16. And when we subtract those together, we have 0.04. Now, 8 goes into 0.04 0 times. We know that. We have to take another 0 here. So we know 8 goes into 0.040, goes into 40 5 times. So what we're left with here is 0, 4, 0, and we are left with 0. We have our answer, so which is 1/8 equals 0.125. Now our first example was really straightforward, but what if we had a different looking fraction that we were trying to make into a decimal? Let's try 2/3. So we're dividing 2 by 3. The numerator is being divided by the denominator. So we're going to follow the same steps here. We have 3 on the outside and then a 2 on the inside. So we go through the exact same steps. How many times does 3 go into 2? It goes in 0 times. We bring down a imaginary 0 here. How many times does 3 go into 20? It goes in 6 times. So we have 1.8 here. Do a little bit of subtraction. We have a 0.2 here now. So follow the exact same process. 0.2, add an imaginary 0. So now we have 0.18 because it goes in 6 times. So we have another 0.02. Now if you notice, this process repeats. We are always left with a 0.2 or a 0.02 or just 2. And then we continue to multiply our 3 by 6 to get our answer. So we always have a 6 up here. And now this process is never going to stop, because every time we add another 0, we are dividing 3 into another 20. So what we have is, in some regard, 18. So we have that 20 minus 18 always leaving us with a 2 moving further and further away into smaller places. Here it's in the tenths place, hundredths place, thousands place, and then so on and so forth. So this process continues forever. So what does that mean? How do we write that? We can't just keep writing 6s forever. So there has to be an easier way to write this. So we know that the 6s will go on forever. There's another form that we can write this to simplify our answer. 2/3 is going to equal 0.66 forever, right? I have the ellipses here, meaning that this is going to go on forever. We can also write this as 0.6 with a line above it. You might have seen this symbol before. This infers that we are repeating the digit underneath the bar here. So this is saying this is 0.6, and the 6s are going on forever. This is just an easier way to write this. Now let's move on to a third example. These are going to get progressively more complicated, so I want to make sure that on this one you're really focusing, because this is a concept that is building off of the others that we have previously mentioned. So another problem, 1 over 18, right? So we're going to divide 18 into 1. So we're going to go through this the exact same way we had done before. 18 is on the outside, 1 is on the inside. Now this time, we know that 18 does not go into 1, goes in 0 times, and 18 does not go into 10 after we add an imaginary 0. So we have to add another imaginary 0. So how many times does 18 go into 100? It goes in 5 times. So what we're left with here is a 0.90, and so we minus that out. So we have 0.10 here, and now we repeat the process again. Drop another 0 down, so we have another 100. That is times a 0.9, and here we have 0, 1, 0 again. And this process, I'm sure at this point you can finally recognize that it will repeat forever, yet again, 0, 0, 1, 0, and then we just continue to do this process forever, 5, 5, so we keep going. But you'll notice something interesting about this problem is this 0 is not being repeated after the decimal place. Only these 5s are. So our 1 over 18 can be simplified as 0.055 repeating, right? With this 5, 5 repeating and not the 0 repeating. Or it can be written as 0.05, and our little bar that represents repeating numbers is only over the 5. So the 0 is here first, and then our 5 is what is repeating forever. All right, Mom, there's just one more example I want to show you. I know these problems can kind of feel pretty long and belabored, but trust me, the process is very important. Once you get the process down, this will help you with a lot of math in the future. Long division is a very important concept. So there is one more problem that I want to go over. I want to do 1 divided by 27. So how is this going to look? We have 27 on the outside and then 1 on the inside. Great. So we should immediately recognize that 27 does not go into 1, and 27 also does not go into 10. So we have to add another 0 here, and we have to add another imaginary 0 here. So how many times does 27 go into 100? It goes in 3 times. So 3 times 27 is going to be 81. Great. So now we just continue like a regular problem. 100 minus 81 is going to be 0.19. We know that 19 is not divisible by 27, so we have to add another imaginary 0 here. 190 divided by 27, that is going to be, the closest to it would be about 7 times. 7 times 27 is going to equal 189. So continue the process, 0.001, 190 minus 189 equals 0.001. Great, but we're not finished yet. We still have this 0.001. So we know that 27 does not go into 1, nor does 27 go into 10. So we have to add 2 zeros here, and so we are adding 1 additional 0 up here. So how many times does 27 go into 100? It goes in, again, 3 times. Now, how do I know that? This is similar to what we did at the start of our problem. We had that first 100, and then we divided that out. We minused out 3 times 27, which was that 81. So let's see if the process will continue. So we know that 181 is the number of the most even number of times 27 goes in there, which is 3 times. And now we are going to continue our process, making sure to keep in mind that we want to keep all of our numbers here in our correct columns to make sure that we are not getting confused. So we have 100 minus 81 is going to be 19, again, similar to what we have up here. 27 does not go into 19 evenly, so we have to bring down 1 additional 0. So now 27 goes into 190 how many times? We remember from up here that it goes in 7 times. So 0.000189, and then Once we do this process again, we will see that we are left at another 1, a 0.000001, but we're back at a 1, so we'll have to repeat the process all over again. Now, you'll notice something interesting about this problem. We tend to always go back to a 1 here. We also tend to see 19 a couple of different times. So this process is repeating. Where is the process repeating? Well, if we look at our answer up here, here we have a 0.037, and then when we get back to our 1 right over here, we do another 0.037. So here the repeating pattern is 0, 3, and 7, and this is going to continue forever. So we know that 1 over 27, that is going to equal 0.037, 037, 037, going on forever because this process is going to repeat. How else can we write that? We can simply write that as 0.037 with the bar covering all 3 of my repeating decibels. In this case, it is 0.037, 0, 3, and 7 are all repeated. And that is the final example.